Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in the last few classes, we talked about some simple distillation operations. We talked about flash distillation. Flash distillation involves a very simple operation where you take a liquid and then you create a partial vapor out of this, and then let the vapor and liquid separate, and then they physically separate and then remove them. Okay, it's a single stage operation, and we see that the purity of the distillate and residue depends on what the feed composition is and how much you vaporize the feed. So that is very simple and easy to design in terms of the process equipment, but it's not give you the pure product, pure A or pure B. Okay, you're limited by the flash operation and the feed composition. Then we talked about the simple or batch distillation, which involves again taking a feed mixture A plus B in liquid form, and then you continue to vaporize and then collect the vapor, condense it and then store it. Okay, so now this is done in a differential manner where the first initial vapor would be very rich in A, but the subsequent vapor will have much lower mole fractions, but then at the end of the operation you get some sort of an averaged distillate composition. Okay, so again batch distillation is slight improvement from flash distillation. Okay, still it gives you little better performance in terms of purity, but from an industrial perspective where you are looking at more pure compounds, neither flash nor simple distillation is good enough. Okay, in terms of throughput of operation, in terms of purity requirements, we need something more sophisticated distillation operation, and that's what brings us to what is called this continuous rectification or fractionation. Okay, these are new terminologies, I believe. It only says that we are looking at an operation which is much more sophisticated, involves multiple stages. Okay, and it involves heat addition, heat removal throughout the column. Okay, so much of the discussion from now on will focus on what do we mean by this continuous rectification, and what are the things that we need to design about, etc. Okay, so essentially this continuous rectification or fractionation is nothing but a multi-stage. It's a multi-stage counter current distillation operation. So as I said before, this is multi-stage. That means there will be several places in this equipment where the liquid and the gas will be brought in equilibrium, and then they are separated, and then they are again vaporized, separated, and so on. So there's a cascade of operation that we are going to look at. That's what's called this multi-stage. And we also say it's counter current, which says something about the flow pattern of liquid and the vapor. Okay. So distillation operation involves two phases, vapor phase and a liquid phase, and we have to worry about what is the flow pattern. Okay, so here in this particular continuous rectification, the flow of liquid and gas are counter current, and of course distillation means that we are going to make use of the relative volatility or more volatile nature of one of the component over the other to enhance the separation. So this is what I have shown here on this figure is a kind of a schematic of a continuous rectification column or distillation column, and it has several features. Okay, so let me walk you through all these details. So first of all, the tall column that you see here, it is a gas liquid operation column. Okay, it's something like a sieve tray column, or it could be a bubble tray column. Its only job is to provide enough interfacial area between the two phases, vapor and liquid. Okay, the tower that you see here is it can be a sieve tray or it can be a bubble tray, and it allows good contact between vapor and liquid. Here the way we operate is that there is something called feed. Okay, so this distillation column operates under continuous mode. Feed is sent in and then the separated products are taken out. So it happens in a continuous mode. This has to be distinguished from the batch distillation, where you start with a fixed amount of feed and then you let it vaporize and separate. Okay, and then you have to remove the residue and distillate and then charge with the fresh feed and then continue. But this, on the other hand, is a continuous operating column. Yeah, in which case? No, that was flash. That is a very special case, constant level, one of the problems that we discussed, right? Yeah, but most of the batch distillations are like single still. Okay, so here what we have is we have this feed, and the feed is mentioned as F moles per unit time. Okay, so this feed will have, mostly it's a liquid, but it can have a vapor, it can have a vapor plus liquid mixture also. But we will say that the feed is characterized by F moles per time, that's a molar flow rate F, and then it has a composition of ZF. Okay, so ZF is based on more volatile species, which is A here. So if this is too small to see, let me just so feed enters here and F is the molar flow rate, its composition is ZF, and in distillation there is also heat addition and heat removal that constantly happens. So we will associate the enthalpy of this feed as HF. So HF would be the heat content or the enthalpy of the feed. And then what you see, this 1, 2, 3, 4, all this horizontal line in this column, these are basically tray locations. Okay, trays are numbered from the top 1, 2, so and so, and then all the way down. And what we have here is, once the feed is entered here and it partially gets vaporized and the vapor goes up, okay, because it's much less denser than the liquid. So because of density, the density difference, the vapor will flow upwards through the column perforations or through the bubble column bubble caps. So if you have to draw, so the vapor goes up through the column, and then when it goes through, and then it goes to the top of the column, and here we have a condenser. The role of the condenser is to take the vapor which is coming at the top of the column at a molar flow rate of G1 with a composition of Y1 and an enthalpy of Hg1. So G suffix denotes is a vapor phase, 1 refers to the top of the column. Okay, those are the meaning of this terminology. So the top of the vapor coming out at the top of the column has a flow rate, molar flow rate of G1, composition of Y1 and enthalpy of Hg1, and then it goes through what's called this condenser, and in the condenser you will send some cooling liquid so as to condense the vapor. Okay, you are going to remove the heat from the vapor so that you can liquefy this product. So here you have kind of a settler. Suppose if you don't condense all of it, okay, if you don't have enough cooling duty, the condenser may not cool or liquefy all the vapor. You may have some combination of saturated liquid and saturated vapor. Then you need something called a settler to separate the liquid and the vapor. Okay, if it's a total condenser, which means all the vapor is condensed into liquid, then you don't need this separator. So you see that once you have condensed this vapor into liquid, you remove that as a distillate, and the distillate is denoted by a flow rate of D moles per time and a composition of ZD or YD, and then you will have a enthalpy of HD. So you can see that the enthalpy is different, HD, from the initial enthalpy because we have removed some heat from the vapor. Okay, that's why the enthalpy is different. So what we are saying, the feed is introduced, vaporized, vapor flows through the top of the column, okay, and then goes through the condenser where the heat is removed, and the vapor is converted into liquid, and the liquid is drawn out as a distillate. Okay, but that's not all of it. What we do here is we take a stream of this distillate and send it back to the column, and this is called reflux. Okay. So, this reflux means the condensed liquid at the condenser, part of it is sent to the column as a liquid. The reflux will always be a liquid, and this liquid will actually flow down the column. So, the blue arrow here indicates the flow of liquid down the column. So, now at a steady state, what happens is that when the feed comes in and then the vapor goes up, there is a contact between the vapor that is rising and then the liquid that is coming down. The liquid is nothing but a condensed liquid called reflux. So, this particular section, the top of the section, we call this as this entire section above the feed line. Okay, from the feed to the top of the column, we call this as absorption section or enriching section or rectifying section. So, the part of the column from the feed location to the top of the column, that part, the top part is called the absorption or enriching or rectifying section. And why we say that is because, since I said from the feed to the top, there is a counter current flow of the vapor and liquid, and the liquid coming out from the top will try to take out some of the B, component B, from the vapor. Okay, so there is a transfer of less volatile compound, which is B, from the vapor to the liquid. That is what we call absorption, absorption with respect to component B. When you try to remove more of B from the vapor to the liquid, the vapor gets more and more richer in A. That is what is called absorption or rectifying or enriching section. We are enriching with respect to A by selectively removing component B from the vapor to the downcoming liquid. Okay, so that is pretty much the operation that is happening at the top of the column. Now, we can say something about the bottom of the column. So, now I am scrolling down from the feed to the bottom. What we have here is, at the bottom we have something called a reboiler. It is nothing but a kettle where we supply heat to vaporize the liquid. Okay. So, this reboiler is very similar to the one that we have in a batch distillation column, where a constant amount of heat is, or some variable amount of heat is given at per unit time. So, the heat duty at the reboiler or a kettle is given as QB, energy per unit time. This much amount of heat is in. So, it can be a shell and tube heat exchanger, or it can be a steam based heat exchanger. Reboiler is nothing but a heat exchanger. So, here what happens is, what is coming down is the liquid. Okay, and this liquid is partially vaporized by the reboiler, and then you send the vapor up. So, in this column also, in this particular column from the feed to the reboiler, that section also, you have a counter current flow of the vapor and the liquid. So, this particular section is called stripping section or exhausting section. So, in the stripping or exhausting section, what is happening is, the liquid that is coming down, in that there is both A and B, and we want to remove some amount of A from the liquid to the upcoming vapor. Okay, that is what is called stripping. Stripping is an operation where a solute is transferred from a liquid to a vapor. Okay, so here in the stripping operation, component A, which is more volatile here in this case, is transferred from the liquid phase to the vapor phase. I know this is little confusing because the notion of absorption and stripping is with respect to different components here. In the top of the column, I said it is absorption with respect to component B, which is less volatile, from the vapor to the liquid. But below this column, below the feed line, we call it as a stripping, but stripping with respect to component A. Okay, we are trying to remove the little amount of A available in the downcoming liquid into the vapor phase. So all we want to is that in both sections we want to enhance A more in the vapor phase and increase amount of B in the liquid phase. Okay, that's all it's all about. Now what we also do here is, in the reboiler, the liquid is partially vaporized and sent to it, and the remaining liquid is taken out as a residue, and the residue flow rate is given as W moles per time, and its composition or the mole fraction of A is XW, and its enthalpy is HW. Now if you also note the notation here in the column, whenever we think about a trace above the feed, we denote the liquid flow rate as L and the gas flow rate as G. And since there may be small variation between the tray, we also give an indication of which tray it is coming from. So we use this Ln and Gn. Ln would be the, let me write, so Ln, this would be the molar flow rate of liquid from nth tray. So this is molar flow rate of liquid from nth tray flowing down, and Gn would be the molar flow rate of vapor leaving the tray N. So L stands for liquid, G stands for vapor flow rates. Suffix indicates the tray from which they are leaving. Now if you look at the trays below the feed, the flow rates will drastically change because the feed will add some amount of liquid or vapor. Okay, there's a drastic change in the flow rates of liquid and gas at the feed tray. So we are going to use a notation L bar to denote the liquid flow rate in the stripping section. So the entire column is actually looked into two sections: absorption section at the top, stripping section at the bottom. In these two sections, because feed is introduced somewhere in between, the flow rates are different now. So you like to distinguish that. So we will use L and G as the flow rates of liquid and gas in the absorption section, and L bar and G bar as the liquid and liquid and vapor flow rates of flow rates in the stripping section. This is mainly because L and L bar, G and G bar could be quite different because the feed is introduced at this point. And another thing to note here is that I also indicated about the heat input and output. In the condenser, we remove heat to the extent of QC, energy per time. In the reboiler, we supply heat to the extent of QB, energy per unit time. Okay, and then all the streams that are coming in and that are leaving out will have an associated enthalpy term. Okay, the feed has an enthalpy, the distillate has an enthalpy, and the residue also has an enthalpy. Okay, so this particular operation has to be dealt with along with the material balance. There should also be an energy balance to this. And another thing is that this entire column may also lose some heat because this column is operating under atmospheric and open conditions. So there can be some convective, conductive, radiative loss of the energy here. So we also associate what is called this heat loss, QL, energy per unit time. Okay. So question for you. So if I look at the temperature variation along the column, where would you expect high temperature? Where would you expect low temperature? But regardless of the feed, let's say a feed is introduced somewhere in the middle of the column, and going from the top to down, would you see a temperature decreasing or increasing? How would it, or the temperature be same? So it's supposed to be more hotter at the bottom, and then as you go up, it will get cooler and cooler. Okay, so the temperature varies such a way that the lowest temperature you will see at the top of the column and the highest temperature at the bottom of the column. Okay. Now, as you can see, compared to the flash and batch distillation, this particular operation is quite involved and quite detailed. because there's a feed coming in, changing the flow rate. And then we look at the section, the distillation section as two parts, where there is this different flow rates flowing in the upper part of the column than in the lower part of the column. It already tells you that you have to deal with the two kinds of operating line. Now, if you remember, the absorption that we discussed again involves a gas liquid kind of an operation. It's a single column. Gas enters at the bottom, leaves at the top, liquid comes at the top and then leaves at the bottom. The liquid and gas flow rate are pretty much fixed, almost constant throughout the column. So you have one operating line, and from that one operating line we have this staircase construction, and to find the number of stages. That is not the reason. The reason I'm saying is that having fixed all the flow rates, if you look at the top of the column, the liquid and the gas flow rate would be of some extent, and then if you come to the below the column, you would have a different gas and liquid flow rates. Okay, and we know the operating line is proportional to the ratio of the flow rates, and you will see two different sloped operating lines. Okay, so that's what we have to deal with it. But before we do that, let us also do some small material balance and energy balance about this column. Then I'll discuss about how to draw the operating lines and find the number of stages. So from the design point of view, what we would like to know is, like in absorption column, what is the number of theoretical stages for a particular separation operation. The column diameter, if you want to calculate, then we have to invoke the concepts of pressure drop for two gas and liquid flows, and we have dealt this with in absorption column problems. Okay, so tower diameter is to be obtained based on pressure drop calculations, whereas the number of stages, theoretical stages, will be obtained from the mass transfer considerations. The approach is very similar to absorption column. Only thing is, here it's going to be a little bit more involved because of the two parts of the column that I was talking about. So now let's introduce some terminologies. I mentioned that here, if you look at this condenser operation, so the vapor that is coming out of the top of the column is condensed in the condenser, and some part of this liquid is sent as a reflex back to the column to enable this absorption operation, and the remaining is taken out as a distillate, which is basically the product that we want. Okay, so we like to basically write what is called this reflex ratio, and this is denoted as with symbol R. R means reflex ratio. This is nothing but L naught over D. Okay, so this is a definition. So L naught is nothing but, as I have shown here, L naught is the liquid that is sent back to the column, that molar flow rate L naught, and distillate is the product that is taken out of the column. This is not coming back to the column, only the reflex is coming back to the column. And the reflex ratio is defined as the liquid flow rate sent as a reflex divided by the distillate flow rate D. And based on this definition, you can see that, suppose if I say L naught is 0, that means I am not sending any liquid back to the column. Okay, so this would mean R equal to 0. Okay, so this is one extreme possibility. Another possibility is that I take D equal to 0, which means that whatever is condensing in the condenser, I am sending the total liquid back to the reflex, no distillate is drawn out. This corresponds to what is called this total reflex, and for this R is infinity. So you can see that the reflex ratio can be operated anywhere between 0 to infinity based on this definition. Operationally, it means what portion of the condensate we are sending back to the column as a reflex and how much we are drawing out as a product distillate. So let's consider this particular condenser section and then write a mass balance. So what is coming into the condenser is G1 moles per time. So let's do a material balance. on the condenser. So I have kind of redrawn the condenser part alone. So you can see that what is coming into the condenser is G1, and then after condensation this is split into two parts, one that is reflex, other one is the distillate product. So if you do a material balance, you will be able to write that G1 is nothing but L naught plus D. So now I can write this L naught in terms of the reflex ratio. I already said I am defining R as L naught by D. So from here you can write L naught is RD, and substituting this in this material balance, you can show that this G1 is nothing but D times R plus 1. Now let us do material balance on species A. In the condenser. So the number of moles of A that is coming in is G1 Y1, and the streams that are leaving out is L naught times X naught plus D times ZD. If you want, you can substitute for L naught as RD and then take D out. So this is the material balance over species A in the condenser alone. Now let us do an enthalpy balance for the condenser. So the enthalpy of the vapor that is coming into the condenser is G1 Hg1, and what is leaving is L naught HL naught plus D times HD, right? What else? The heat removal, right? That is QC. So generally we are interested in calculating how much is the cooling duty for the condenser, and if you want to obtain, this is the energy balance you should be doing, and then you can write QC is equal to G1 Hg1 minus L naught HL naught minus DHD, and we already know that G1 is, from the material balance we found G1 can be written in terms of reflex ratio as D times R plus 1. So I am writing G1 as D times R plus 1 Hg1, and L naught is nothing but R times D minus DHD. So D can be taken out. So you obtain the condenser duty by this equation. So you can see what this depends on. This depends on what is the reflux ratio and the enthalpy of three streams. What is the enthalpy of the incoming vapor, whether it is saturated or whether it's superheated, that kind of is given in this Hg1. HL0, HD, these are all the enthalpies of the liquid and the liquid reflex and the distillate. Like I said, whether it is a total condenser or whether it is a partial condenser depends on these factors. Okay. So if you want to have all of them condensed, HL0 and HD will be equal and they may be related to the saturation liquid enthalpy, and you can calculate QC from here. Okay. So QC is one of the important things that we may want to calculate. Now similarly, we can do heat duty calculation for the reboiler also, because reboiler is also involved in vaporizing some of the vapor, some of the liquid, and we need to find what is the heat duty for the reboiler, and we can obtain that by doing an energy balance on the reboiler. Well, let us do for the entire column, energy balance for the entire column. So schematically, I will redraw here again. So feed is coming with F and HF, and you have got the condenser and the distillate. So you have a reboiler here and residue here. So HW, yeah. So heat supplied to the reboiler is QB and the heat removed in the condenser is QC. So the entire column now is schematically shown here, paying attention to only things that are coming in and things that are going out. Heat loss also is there, yes. So we will say that is QL. This is heat loss. So heat loss not necessarily happening from the top, it is basically throughout the column. Heat loss happening also in the reboiler, okay, for the entire column. So here we can do the energy balance for the entire column, not paying attention of the localities and what happening inside the column. So looking at only streams that are coming in and coming out, going out for the entire column. So if you see what is coming in, you will see that is feed coming with an enthalpy of HF. Okay, so this much heat is coming to the column, and then QB is also coming into the column through the reboiler. So these are the two heat addition into the column. One is heat is imparting some heat, and the reboiler is also adding some heat to the entire system. And what is going out is there are two product streams, D times HD and then W times HW. So these are the enthalpies associated with the distillate and residue, plus the heat removed in the condenser, plus the heat that is lost. Okay. So from here you can solve for QB. So the point of doing all this is that you should be able to take a particular section or the overall section of the entire column, and you should be able to write overall material balance, species material balance, and energy balance. Okay, and these are all coupled. For example, if you want to calculate QB, it is not enough to know only the enthalpy terms HD, HW, but you also need the distillate flow rate W, the residue flow rate, distillate flow rate D, and the residue flow rate W, and so on. So, okay. So in a way that energy balance and material balance will have to go hand in hand in terms of designing the distillation column. So from here onwards, in terms of like I said, the design issue here is to find the number of trays, okay, number of theoretical stages required for the separation. There are actually two famous methods. One is called the sponge and Sauerett method, which involves the simultaneous enthalpic and material balance calculations at every stage. The other one is called McCabe-Thiele method, which is more simpler, and it is something that you can do it graphically, okay, and does not involve too much of enthalpy calculations, okay. It involves only the overall energy balances. It does not involve how the enthalpy is changing at a stage to stage level, okay. So that's why it's much more simpler, and in view of the time that we have in hand, we will talk about the simpler method called this McCabe-Thiele method to calculate the number of stage. So I'll talk about this calculation in the next class, but just to give you, just to sensitize you, what we are hoping to do is, we would like to kind of have the equilibrium diagram, okay. So as I said, for any design calculation, the equilibrium line is very important. So here the equilibrium line is Y versus X. It relates the vapor to liquid composition equilibrium. And what we will do is, we will draw two operating lines. Like I said before, that the distillation column involves different flow rates. So we'll have one operating line like this, and another operating line something like this. So the top, the red line will be drawn for, let's say, the absorption section at the top of the column, and the purple line is actually for the stripping section at the bottom of the column, okay. So you can see that there is an equilibrium line and there are two operating lines, and what we would like to do is to start constructing the staircase diagram like this, and then find the total number of stages, okay. So now if you see, I have to take a transition from one operating line to the other operating line at the right point, okay, and that becomes a very critical issue. And the slope of this line also depends on what is the reflex ratio I am using, okay, because the slope of the operating line is proportional to L/G ratio, the liquid to gas flow rate, and that is in turn determined by the reflex that you are saying. So depending upon the reflex ratio, the slope will change, and the intersection point between these two lines will also change. So there are a lot of interesting questions to be answered, that how do I choose the reflex ratio? It has a range from 0 to infinity. What is the optimal reflex ratio to use? Once you do that, then the operating line slope will be different. Where do they cut? And what is the quality of the feed? Is the feed is always a liquid, or is it always a vapor, or is a mixture of vapor and liquid? And how do we deal with that? Okay. And the other question we would like to ask is, how to find the feed location? Okay, those are interesting questions we have to pose. And then the next class, I will talk about these things in detail, how to draw the operating line for the absorption section and stripping section, how to find the feed location, and how to take care of both operating line in determining the total number of stages. Okay, this is called this McCabe-Thiele method. So we'll discuss about this in the next class. For now, it's over. Yeah, thanks.